Today, we're tackling a problem that seems simple on the surface, finding the sign of a product of numbers in an array. The catch? The numbers can be large, and the product could easily overflow standard integer types. How do we determine its sign efficiently? Given an integer array, nums, we need to return 1 if the product of all elements is positive, -1 if it's negative, and 0 if it's 0. The core challenge is handling potential integer overflow if we were to compute the actual product, making a direct calculation problematic for large inputs. We only care about the final sign. A naive approach might involve using a large number type, like a big integer in C#, to store the running product. We'd initialize a big integer to 1, then iterate through the array, multiplying each number into our product. Finally, we check if this big integer is greater than, less than, or equal to 0 to return the appropriate sign. While this works, big integer operations are significantly slower than primitive types, leading to higher constant factors and potentially affecting performance for very large arrays. Its time complexity is roughly big O of n with big integer overhead, and space complexity is big O of 1, constant time for the single big integer variable, though its internal representation can grow. The key insight here is that we don't need the actual product, only its sign. The sign of a product is determined by two factors, the presence of 0, and the count of negative numbers. If any number in the array is 0, the entire product is 0, so we can immediately return 0. Otherwise, the sign depends solely on how many negative numbers there are. If there's an even count of negative numbers, they cancel each other out, resulting in a positive product. If there's an odd count, the product will be negative. So, our optimal strategy is to iterate through the array once. We maintain a counter for negative numbers. If we encounter a 0, we return 0 immediately. If we find a negative number, we increment our counter. Positive numbers don't affect the sign, so we ignore them. After iterating through the entire array, we check if our negative count is even or odd to return 1 or -1, respectively. Let's trace this with the example, -1, -2, -3, -4, 3, 2, 1. We initialize negative count to 0. First, we see -1. It's not 0, it's negative, so negative count becomes 1. Next, -2, not 0, negative. Negative count becomes 2. Then -3, not 0, negative. Negative count becomes 3. -4, not 0, negative. Negative count becomes 4. Now, we encounter 3, not 0, not negative. Negative count remains 4. Similarly for 2 and 1, negative count stays at 4. After the loop, negative count is 4, which is an even number. Since 4 is even, we return 1. The final answer 4, -1, -2, -3, -4, 3, 2, 1, is 1. This is correct because there are 4 negative numbers, an even count, making the overall product positive. You'll spot this pattern when a problem asks for properties of a product or sum, but explicitly warns about potential overflow, or when the magnitude of numbers is irrelevant, only their contribution to a final state. Anytime a problem asks for the sign or parity of a large aggregate value, think about counting negative numbers or zeros. The time complexity is big O of n because we iterate through the array once. The space complexity is big O of 1, constant time as we only use a single counter variable. Mastering the parity trick is crucial for these types of problems. Try the next problem, same pattern. Don't forget to like and subscribe for more efficient algorithm breakdowns.